recap whatever was done in the previous lecture. So in the previous lecture, what we did was we kind of, went through all these memory elements that are shown here. So we started with SRAM. We told that, okay, since it requires 6 transistors to store 1 bit, so its area is very high and we cannot achieve very great densities with it. Also with the scaling technologies, the static leakage power of SRAM is quite high. And therefore from power perspective, as well as from an area perspective, this is something which is not actually preferred for creating large memories. However, it's very fast. So it's still used for cache memories and, close to the computing core. Then we discussed about DRAM, that the problem with DRAM is scaling, because scaling of these capacitors is a big problem considering the peripheral circuitry and all. And also these transistors are leaky and they're getting more leaky with, I would say, developing technologies. So this kind of hinders the scaling of this DRAM technology. Then we talked about this flash. So these two form under a class of volatile memories. Then we talked about some non-volatile memories. Flash was one of the most mature technologies that we talked about. The problem with flash is again scaling. So what happens is when you scale the flash devices, the neighboring transistors or the neighboring flash memories are placed so close to each other that if you apply a voltage on one control gate, you kind of have some interference in the neighboring flash transistor. So because of this, they're not scaling it down in the horizontal direction now. Instead, what they're doing is they are kind of stacking it vertically in the form of 3D NAND flash memory. We'll talk about that later in a special module for that. Then we also discussed about these RRAMs or resistive based memories. In that we talked about MRAM, how basically spins can be used for storing any bit in the form of resistance states. But the problem with MRAM was that the TMR ratio is pretty low. The R on by R off, or the memory window is pretty small for this. And for SRAM, where there is this read-write dilemma, but for MRAM there is a trilemma, which is called read, write, and retention trilemma. So we'll come to that when we discuss MRAM in detail. Then we also talked about this phase change memory. And the problem with the phase change memory is that we need to inject a huge amount of current to heat this phase change material and to change its phase. So the current is one of the major, like a high current is one of the major, I would say, limitation to this phase change memory. Otherwise, it's a very scalable memory, and for large storage or dense storage, this is the memory that most probably we'll get into in the future. Then we also talked about this RRAM and CBRAM, where a filament is formed between two electrodes. And the major problem with RRAMs or CBRAMs is the variations, the device-to-device variation. This conducting filament formation and dissolution is a stochastic process. So for different devices, and even for the same device, if you apply the same voltage at different instances of time or during different cycles, you'll get some different kind of formation of this filament. I mean, sometimes it would be like this, sometimes there would be multiple filaments, and all sorts of things happen. And because of this variability, their applications are restricted. So the different memory characteristics that we looked at was first cost. Cost should be as low as possible. The program or read power, because every time you have to program the memory or you need to read the memory. So the kind of power that is kind of required for each program or reading step, that is very important. Then we also have some other component of power, which is called the retention or standby power. Even when your memory state is in hold, it will consume some amount of power. That is also a very important part. Then there's this operating voltage or current. So how is it different from these power cells? Operating voltage basically determines what is the supply voltage that you need to give to that chip. For instance, your flash memories or even your 3D NAND flash memories, they require voltages in excess of 16 volts on chip. But the kind of VDD that you provide them, for instance, let us say that we are working with our 28 nanometer technology node, or let's say 14 nanometer technology node, where our supply voltage is 0.9 or 0.7 or something like that. Now, if you somehow integrate flash memory on that chip, and if you want to give them 16 volts for programming, how will you do that? So that is where this operating voltage or current comes into picture. You can either use a charge pump circuitry, or you have to add another supply which is 16 volts or something. So that is how you basically work with this operating voltage. That is why you need this operating voltage and current. Now speed is something, or speed or access time is something that is really important. Then endurance, basically endurance means how many number of program or erase cycles you can continuously cycle your device before it fails. So typically what the industry says is 10 per 6 cycle or 10 per 7 cycle is fine. It's fine for them. Then again, density. Density is something which also dictates your cost. The more dense your memory, the less costly it will be for the same amount of memory. And density is something that is really important for standalone memory business, while it is not of that importance for your embedded memory applications. Then scalability. Scalability is kind of potential for future further scaling. I mean, your RM devices are 2-terminal devices. They are occupying your 4F square area already. However, your transistors and all, they occupy a very large area. They are the minimum size transistor that you can get is something like 6F square. So these RRAMs kind of occupy a very small area as compared to your transistors, and their potential, like as you reduce the F, their scalability will kind of improve. And also you can improve their scalability further by 3D stacking them. And in that case, if you have stacked L layers, your kind of density becomes 4F square by L, and you have inherently, or you have in other words, you've actually scaled their dimensions by F by L, F by root L, I would say, if you do the calculations. Then other point, or the other important point for memory, is retention. So retention is how long your data can be held onto that memory when the power is turned off. So the industry standard for retention is 10 years. If your device can hold any memory state for 10 years, then industry will accept it. Then reliability. Obviously, reliability is important for it should be reliable. It should not fail during its operation and all those things. Temperature resiliency. See, many of these memory elements, or in your processor or even in your automobile applications, the processor heats up, and the temperature on the processor goes till 125, 170, or even 200 degrees or something. So your memory should be such that it can work efficiently even at such temperatures, even at such high temperatures. Then radiation hardness. What I mean by radiation hardness is any impact of alpha particle, gamma particle, or any other radioactive element, it should not impact the state of the memory. For instance, your packaging materials, or if you are using your memory for some extraterrestrial applications, such as you are sending your space rover, you have some memories on it, and you are sending it to Mars, or you are sending it to on the moon or something, and then there are a lot of gamma rays in the space. So if the gamma rays hit your memory, what exactly happens is it leads to creation of electron hole pairs, and it leads to a phenomenon which is known as single event upset. So that should not happen. So your memory should be resilient against this radiation. So that is what I mean by radiation hardness. Then it should also be CMOS compatible, because CMOS technology has been established, and no industry would really change their entire fabrication technology and move to some other kind of technology. So if it is CMOS compatible, the industry will readily adopt it, and that is why I included this in the preferable memory characteristics. Then EMI and EMC was also a very good point which people brought to notice. Then comes memory window. So memory window, if it is very small, by memory window I mean the kind of sense margins or something like that. So if the sensing margin between bit 0 and bit 1 is very small, you need extra sensitive sense amplifier, or you need a sense amplifier with a very high gain. However, if your memory window is large, you can somewhat relax your peripheral circuitry requirement. And in all these memory circuits, what you want is that your memory block should occupy the entire area, and your peripheral circuit area should be as low as possible. Then multi-bit capability. So it would be always good if your one memory element stores not only one bit, but it stores several bits. By several bits, what I mean, how can one device store several bits? So if it is going to support 2 bits, then there has to be 2 different memory states, or 2 different resistance states, or 2 different threshold voltages that it shows. However, if it shows more than 2 states or more than 2 threshold voltages, then it can be used for storing multiple bits. For instance, nowadays your 3D NAND flash memories, they're coming with 4-bit capability. So each of these cell can store 4 bits, or it can show 16 different threshold voltage characteristics. Again, there's something which is known as variability. So for CMOS circuits also, or for digital circuits, or whatever you take into account, what you want is that your transistors, your neighboring transistors, should be matched. Their properties should be as close to each other as possible. However, that is not possible because of process variations and random dopant fluctuations and all those problems, all those sources of variability. But even in memory, you want that different memory elements on your array or on your chip should be as matched as possible. Then there should be flexibility in interfacing. There should be flexibility in topology, whether the memory element requires a selector device or not, because if you add a selector device, you are definitely going to increase the size of your memory, and as such your density will suffer and also your cost will suffer. Then addressability, whether you want your memory block to be erased whole at a time, I mean erased parallelly at a time, or whether you want to erase individual blocks at a time. I mean, depending upon different applications, you want different addressabilities. For instance, if you want to have a standalone memory, then you would want to program them parallelly, you would want to erase them parallelly, and you won't be kind of interested in programming them bit by bit. But when it comes to applications such as neuromorphic computing, you would want since the weights there, like the neural network weights there act like synaptic conductances, or the resistant states of these memories. There what you would want is, there you would basically want this bit addressability. So that is what you will want there. And last point, security. So security is something that you really want. You don't want some attacker or some malicious software to kind of get the data which is present in your memory. Mostly people will use this security primitives at the system level, but with this advent of new memory technologies like RRAM and all, you can even embed it within the memory block itself in the form of hardware security primitives. First, before getting into details of SRAM, we'll go about this memory architecture. So how basically large memories are kind of organized is, first we organize different bits as words. You must have seen that different bits are organized as bytes. So 1 byte is like 8 bits. So along the same lines, we basically organize these bits as words. Nowadays, you have a word size of 32 bits if you're using a 32-bit computer, or a word size of 64-bit if you're using a 64-bit computer. Then let us take a case of n-word memory with each word consisting of m bits. Here m bits, m can be 32 or 64 for your modern computers, but let us just generalize it as m bits. And let us say that we have n such words. Now the most intuitive way of organizing them is, let's just stack the words on top of each other. So we have like n words here, each word consisting of m different bits, and each of these bits are basically represented by one storage cell as shown here. Now how can we address this kind of a memory? We have several select lines, like n select lines to be precise, which are actually addressing each of these words. However, if the memory is very large, if the memory size is very large, what happens is, let's say we talk about 1 megabyte memory itself, which is very small nowadays, but let us talk about 1 megabyte memory itself. So each word is like 8 bits, and we have like 1 mega words. So your n is 2 raised to the power 20. So if you want to root it in a chip, so if you want to have 2 raised to the power 20 lines in your chip, it becomes really difficult. And for routing this 2 raised to the power 20 lines, you also need 2 raised to the power 20 pins, because each of these selectors are basically given by some pins through the external world. So that is also a big problem. So how they basically come over this is by the use of a efficient peripheral circuitry. So what they use is a row decoder. So how row decoder works is, it kind of compresses your number of pin required from n to log base 2n. So now you just give an address, which is kind of k, which is nothing but log base 2. So you give it a k bit address. It selects one of those n lines, and then it selects a particular word. So by just using this row decoder, what we have done is, we have reduced the number of pins from n to log base 2n. And also, one requirement over this row decoder is that it should be pitch matched with this memory block. Why it should be pitch matched? So that these selector line lengths should be very minimum. I mean, they should not cross over one another, and this length should be very small so that we get a very fast access time. And we also get a very low loss, which is happening in these lines. So that is why your peripheral circuitry has to always be pitch matched with your main memory. This is a very general requirement of any memory block. Layout of this memory cell, what you should ensure is, whatever height of your height of your memory block is there, the row decoder should have the same height, so that the interconnects have very small length to traverse. That way you kind of cut on your interconnect delay and interconnect losses. However, if you look at this configuration, although it's pitch matched in this direction I would say in the width direction, but all the input and output pins have to access all these words, right? So for some input output bits, so for some words, the length is very large along this direction. However, for others, the distance is small. So the interconnect requirement is very large along this direction. Although it is very small in this direction, along the horizontal direction, it is very large along this vertical direction. So what they do is, they basically arrange it in the form of array. So how they do it is, they basically try to keep the aspect ratio close to 1, and they include several words in a particular row. So earlier we had only one word in a particular row, like this. Now what they do is, they kind of arrange several words in a row, like this. And they come up with an architecture where your aspect ratio is close to 1. So by doing so, what we need now is a column decoder as well, which can kind of decode one particular word in between different these columns. So now how we define these bit lines and word lines? So we had already used this term bit line and word line in our first lecture or second lecture. So now how we define this bit line and word line is, these select lines which go to your words are basically called the word line. And these column lines, which kind of select one word out of these several words in the row, are known as bit lines. So that is how you define your bit line and word line. And this is kind of a general form in which your memory is kind of arranged. Now, how even some big memories are arranged? Can we have any further simplification? Yes. So large memories are further divided in several blocks. How? So we have, apart from this row decoder and a column decoder, we also have this block decoder. So we have several blocks of similar kind. I mean, this is one block. So we have several blocks like this. What this block helps us to achieve is, first, there are some local word lines and local bit lines in the block. So we have a fast access. So each of these blocks has its independent row, like row decoder and column decoder. And because of that, you have a faster access to this. Instead of one wire going from here to here, if a wire is directly going from, you have these local word lines and bit lines for each of these blocks. And because of this, what happens is, you can have a very fast access to this memory block, all the elements of this memory block. And also, as I discussed last time, that there is something which is also called power gating. So, with power gating, what you can do is, suppose we need to access the data which is present here, and we do not need all the data which is present in different blocks. So if the entire thing was arranged in one block, you would have to kind of like select the entire memory at once, and you would dissipate a large amount of power. But with power gating, what you can do is, you can actually power gate these non-active blocks, and as such, you can actually save a lot of energy. So that is also an advantage of dividing this large memory into several blocks. Now let us look at the role of a peripheral circuitry. So when you talk about digital circuit, when you design a digital circuit, what you think is, it should have a very high output swing. The noise margin should be very high. The inputs and outputs should be isolated. There should be large fan out. And even, the speed should be as fast as possible. So if you take all these design considerations into account, what you will come up with is one element which requires at least 22 transistors for storing one bit. So how the memory designers like overcome this is, for memory, what they want is, your density should be very high. The memory core should be very high. Like the density should be very high. So if the memory core should be heavily dense, it cannot work with one bit being stored in 22 different transistors. So you need to reduce the number of transistors. So, okay, if you reduce the number of transistors, what happens is, you kind of degrade these performance on these kind of parameters. So it's like there's a trade-off between the performance and the density. So how you can actually work around this is, you can use peripheral circuitry to regain your performance. So memory designers are very clever. Memory designers come up with very good peripheral circuitries, and then they kind of, even though your individual memory blocks are not that good in terms of these digital circuit considerations, the overall, I would say, to the external environment or to the external user, it appears like the memory is kind of robust to all these parameters, just because they have designed their peripheral circuitry in a very good way. Let us say we take a simple case where, just to reduce the dynamic power and reduce the delay in charging and discharging of bitline capacitance, we have reduced output swing on BL. I will discuss why we have a swing on BL or why do we have a bit line capacitance and all later. But let us say just to reduce the power and just to reduce the delay in charging, you reduce the output swing. So you reduce the voltage, you basically reduce the dynamic power, and you reduce the delay in charging and discharging any capacitor. But at the same time, what you want to do is, to the external world, your output should look like a rail to rail swing. I mean, the external world would understand only VDD or zero if it's a digital circuitry. There comes the role of this sense amplifier, and the peripheral circuitry such as sense amplifier, or even your charging, pre-charging and all those schemes, they can really help you improve the speed and give you rail to rail swing. Now, this is the major role of memory designers. I mean, you must be, like, many of you may be going to this memory design companies, and there the main role that you will be doing is you will be optimizing the core arrangement, the arrangement of the memory core, as I discussed, like your aspect ratio and the decoder design, the sense amplifier design, your drivers design, and all those things. And you would also be playing with these peripheral circuitries to further improve the performance of your memory blocks, which is a 60 SRAM cell. So what happens in a SRAM cell is you have this cross-coupled inverter pair, which you can identify like this. This is your cross-coupled inverter pair. And then you also have this 2-axis transistors. So this M1, M2, M3, and M4, these form the cross-coupled inverter pair. M5 and M6 are the access transistors. So there is this read and write conflict in SRAM, which I'll be discussing in detail. One more thing that I'll want you to know is, since this bit line is connected to several such SRAMs, so this is one SRAM block. So this is one SRAM block. Let me just remove this. Yeah. So this is one SRAM block. Several such SRAM blocks are placed on this bit line and bit line bar. So we have several such SRAM blocks. And we also have this capacitance over here. Like you see, there is this capacitance over here, which is nothing but the CGT. We also have this CGT over here. So the kind of capacitance that this bit line sees is n times that CGT, right? And there would also be some sense amplifiers connected here. So there would be some pre-charging circuitry, which would be connected to these two lines, some pre-charge, and also some sense amplifier, let's say SA. So these two also will have some capacitances, and because of this, and also there would be this line capacitance of this bit line, the interconnect that we have, there will be some line capacitance of this. So we kind of merge everything together, and we call this CBL and a CBL bar. So that was the bit line capacitance that I was talking about in the previous slide. So it's kind of the summation of all these capacitances that this node sees. This node sees different CGDs. This node sees different pre-charge circuitries, input capacitance, sense amplifiers, input capacitance. So this CBL is kind of the overall, I would say, combination of these, all these charges, all these capacitances. And the CBL for modern SRAM cells is in some picofarads, is in the range of some picofarads. So there's this read-write conflict in SRAM, which is really important. And if you see here, this SRAM works with two bit lines. One is bit line and one is bit line bar. So the thing is, do we really need two bit lines? Like, do we really need bit line and a bit line bar in SRAM? If we do not need it, why do we use two bit lines? And can we work with only one bit line in SRAM?